It involves the logic. I mean, 1 to 0, 0 to
So you give an input 1, it gives an output 0. You give an input 0, it gives an output 1. Something like this. Huh? So this is the BJT inverter. This many people would have studied in their earliest electronics course, because BJTs are the bread and butter of first year courses. Few places BJTs are not even talked about. People only talk about CMOS only. But yeah, this is one of the oldest implementation of an inverter when CMOS did not exist. Only BJTs existed. So what we said was that if you increase VI, what happens? The current that can flow through this BJT increases, and therefore V out goes to 0. And this is the transfer characteristic. What does it mean? How will a change in VI transfer to a change in V out? That's why it's called transfer characteristic. Clearly, you cannot get a very clean 0 over here, because there is some resistance of this BJT that will come into picture. And also there is a continuous flow of current. Are you able to see this?
Yes, sir.
So not really the best way to design an inverter, especially in today's technologies. So we come to MOS inverters. Let us say this is something we do. So over here again, you will notice that there is a continuous flow of current that will happen when the output is intended to be kept at 0. When V out is expected to be 0, then there is a continuous flow of current that will happen from Vs. So we move to what is called as CMOS. What is the beauty of CMOS? That when the input is 0, the PMOS is on and the NMOS is off. So what happens? Once you charge the output capacitance, no further current would flow. You know this, all of you? Meher, you have a question?
Yeah, sir, about BJT inverter. So from our previous courses, what we read was that we used to bias our BJT to a particular voltage, and then at a particular bias point, and then we used to give it small signal voltage as an input.
That's the small signal analysis. That's a small signal analysis, Meher. अभी हम उसको इन्वर्टर लॉजिक ही चेंज करने की बात कर रहे हैं.
Yeah, yes, exactly. So that was my question. Can we apply digital logic into such a?
Yeah. So जब तक MOSFETs और CMOS नहीं था in 70s, BJTs were the only devices, so they were used to make inverters.
Okay, but we cannot do that through small signal analysis.
You have to go to large signal analysis then. However, today we largely talk about small signal analysis in BJTs because we know that full swing करना है तो CMOS है ही.
Okay.
In fact, today we talk of even small signal on CMOS only. BJTs are avoided because they simply have a lot of gate current and other inefficiencies in there. Yeah, that is probably the only place that BJTs are used for analog circuits, where small signals have to be handled very carefully. You need lots of gain and everything. Can't do without a BJT then.
And sir, what were the disadvantages we were facing, like in the previous slide when we use MOSFET technology, for example, NMOS? So yeah, what were the problems we were facing?
So tell me, I've put a 1 over here. So what happens? This device is fully on, it will sink current, and this will continue to provide current. So there's a short circuit path.
Oh.
So when my output is intended to be 0, there's a short circuit path.
Right.
So again, when the PMOS was not being able to be manufactured, this was still better than BJT. But now that we also have PMOSs, we only use CMOS.
Okay.
And this part, one on the right, you already know very well, isn't it? We've discussed this in detail. What is this?
The layout of inverter.
Layout of an inverter. And there could be another layout of the inverter where, so if you want to connect two inverters, you simply abut them. you know. So we discussed abutment. You simply abut them, and the output of one you short to the input of the other, and bingo, you have the output there. In fact, ये वाला wire भी already exists करता है. You only need to make this connection, and your two inverters are connected into a buffer. VDD and ground already shared because they get connected like this. You're able to relate this? We've already discussed this in the class. In the class also, office has also multiple times. And
Sir,
this is the inverter with a strap, where we say that, okay, I will also have a strap within the standard cell. And we already agreed that this is no longer a good idea because you see this kind of height is wasted. So we said that, no, we will not do that. We will, in fact, have it like this only, where the straps will be added later. You remember this?
So in this only, sir, how is this? What is the strap part here in this?
This part.
Yeah. Okay.
So this is the NMOS, but you notice they have a N plus over here instead of P plus.
Yeah. Yeah. Yes. Sir.
So this
So,
becomes the strap connection. Yes.
so what would happen in normal standard cell would be that inverter would be running over the ground, and at some place along the line, the strap would be placed, and it would not occupy a specific area like it is occupying here. Is that my correct?
So for example, if I have to put a strap, I will simply add a strap cell here. And over here, there will be, what do you say? The substrate connection for the PMOS, N-well, substrate connection for the P-well, and the VDD and ground will go ahead like this, and then you will have another cell that you could put over here, and so on. So, आपका सवाल, did I answer you, or did I answer something else completely?
Sir, okay, I got it. I got my point. Yeah.
Okay.
sir, I have a question on same slide.
Yes.
Sir, here you have drawn OD, the yellow one and green one. So in that OD, you have made a L type of cut. So, sir, this L type of cut, sir, would this be feasible in that technology? I mean, that
Yeah.
this.
Yeah. You can do that. We would want you to avoid it. In advanced technologies, we would want you to avoid it. But in earlier technologies, just to reduce the source and drain capacitance, source and drain leakage, basically reducing the source drain area, we would do that. No challenges. We can do that. In 65, you can do that.
Okay, sir. And sir, in
18, you will not be allowed to do this.
Okay. Sir, in the next slide that you showed, the strap one. Sir, there you have drawn a NP layer and PP layer, very small layers. But sir, it has a minimum DRC of minimum area. So can we draw it inside like that, very small?
No. So this is for a still older technology. You may say this is a 1 micron technology. You see, or this is 0.6 micron technology. This is very old technology. In those technologies, it was possible. That was the way it was designed. Okay.
One more question. Like we use these two inverter layouts for buffering. That's primary purpose. Because
I'm sorry, दोबारा से बोलो. When do we use those two inverters?
Two inverters, yeah.
Buffer, to make a buffer.
Yeah. That is.
Back the two inverters right one after the other so that we have a buffer.
सर
Yes, Divya.
सर ये बेसिकली स्ट्रैप है क्या, लाइक इसका यूज क्या हो रहा है इसमें?
तुमने 3 बार डिस्कस करा दिव्या. So you remember we talked about latch up and reducing the substrate resistance?
Yeah, I remember.
So the straps are providing the VDD and ground connections to the substrates, na?
Okay.
याद आया?
Yeah.
Yeah. So this is for substrate connections. Straps are substrate connections.
Why do we have moved poly to left side? It was in middle previously.
I'm sorry?
That polysilicon was in middle, the red color in the previous slide. Now it moves to left side. Is there any specific reason?
No specific reason. This is the kind of layout you will use today. This is just how it was used to. It could have been done and was probably done earlier. Today you will see that poly will only be vertical. You will not be even allowed to route poly in two directions. So that this is the layout you will end up using anyway. Earlier, okay, people thought that, okay, I will simply make, I don't even need to make an extra wires. You see, the out is going out till here and the in is also connected by metal to here. You just abut them and they get connected. So that was the intent at some point of time, but not really needed. Moreover, they wanted to make butted straps. So source ke saath hi they just butted the strap region. Today straps are not handled like this at all. So it's really not a challenge. Okay. Faisal?
Sir, on the inverter, when we were drawing a single inverter, I think you were explaining the circuit of the inverter with PMOS and MOS. So can you please explain the circuit?
Circuit of PMOS and NMOS?
Yes, sir.
Just come to the, you're talking about response time or something like that?
Yes, sir. So you were explaining the capacitor will charge and then someone asks doubt.
Don't worry, you will not miss anything.
Yeah, this circuit.
हाँ, तो इसमें क्या?
I think you were explaining.
You're saying that when the input is 0, the PMOS is on, NMOS is off.
Yes, sir.
So the capacitor will charge and that's it. No further current.
हाँ.
Okay. Whereas in BJT and MOSFET, MOS inverters, there was a continuous flow of current.
Yes, sir.
So that is the beauty of CMOS.
Okay, so that's
that
it.
Current goes only during the transient period. After that and before that, current is 0. Whereas in BJTs and other places, the current will flow for continuously when your input is, let us say, 1 or 0, whatever.
Okay. Okay, sir. Thank you.
Yeah. Rajneesh, you have a question?
Yes, sir. Sir, in the previous slide, sir. Sir, when I was doing some the custom layout, sir, in that when over the OD, when I was doing this, making the source and the drain, then sir, this non-butted error was coming, DRC. So, sir, I was not able to figure out that what was the mistake in that. Sir, when over the OD, I was making the source and the drain, so then this non-butted DRC was coming, that it is non-butted. So I was not able to clear it, sir.
Non-butted DRC was coming?
Yes, sir, it was written non-butted, sir.
So did you put the proper straps in your circuit and everything?
Yes, sir. But yes, sir. Straps are put in, yes.
So I don't know what exactly this would mean. So just check the language and check with others also.
Okay, sir. Okay, sir. I will figure it out, sir.
Yeah.
Okay, sir.
Okay. Yeah. So now we come to the DC response. What do you mean by DC response?
So I mean, we give input as a DC signal and we see its response by the circuit.
Yeah.
In the DC domain itself.
If my input is held constant at a particular voltage level, at what voltage my output would be held at? That is my DC response. I'm not talking about transitioning from 0 to 1. I'm talking about if my input is at, say, 200 millivolts, where will my output be? For example, we are saying when Vin is equal to 0, the output, when Vin is equal to 0 or Vin equal to VDD, the output will be VDD or output will be 0. That is DC. And in between these, it depends on the transistor size and current. such that the current from the NMOS and PMOS is balanced. Are you with me? Over here in DC current, any capacitance or anything else doesn't even come into picture, because talking about all transient being taken care of, and now where does the value stabilize?
So what do you mean by the balancing of this ITS, DC, PMOS current and MOS current?
You tell me. There is this node. What is the Kirchhoff's current law according to this node?
Incoming.
What does Kirchhoff's current law say?
Some incoming is equals to outgoing.
Yeah. So where all the current could be coming in here and going up from here? Only these two NMOS and PMOS, no?
Yeah, yes, sir.
So we are saying that Kirchhoff's current law cannot be violated.
Okay, okay.
That is all, nothing else. Okay. So let us look at this much, you know, what is the cutoff region, what is the linear region for the NMOS, what is the saturated region for the NMOS and the PMOS also. So PMOS is simply the dual of this. You remember this much?
Yes, sir.
Huh? So yeah, the PMOS is simply the dual of that NMOS wala cheez. If we try to make the current curves, IDS curves, IDS, VDS curves for different VGS values, this is something what you would get. Provided that you are saying that beta n is equal to beta p. So VGS P5 will be equal to, or the current at VGS P5 in magnitude will be equal to current at VGS N5. Is this okay?
So beta factor is
beta factor is that over here we are saying that current at a particular VDS has been equalized by changing the width, by making the PMOS wider. There is a ratio of mobility. The PMOS has lower mobility. The holes in the PMOS, the carriers in the PMOS have lower mobility than the carriers in the NMOS. So that you compensate by making the PMOS wider. So that overall beta that comes in the current equation is equal.
This beta is K and C of omega by L.
Yeah, and also includes W and L into it.
Okay.
Sir, actually, I'm not able to get what exactly we know beta here. Like you.
Arey bhai, so this current, what is the current equation?
Yeah, W, K and W by L.
And then VGS minus VT, the whole square something. All this is being put as beta.
Okay, okay, fine, sir.
Okay.
Okay.
So we are simply saying that you size the PMOS up in such a way that K1, K2 या mobility का जो भी difference है, that is compensated for.
Okay, okay, sir, got it, sir. Thank you, sir.
So this is how your IDS, VDS curves would look like.
Yes, sir.
Huh? So if we now plot them for a circuit per se, what would happen? We said IDS and IDSN and IDSP should be equal. That is where I will get to know where my device is in different positions. Am I right? That was what we said. So yes, I would essentially need to plot IDSN and absolute value of IDSP one over the other to get something like this. Are you with me? Huh?
The y-axis is it's a ratio, or like there are two different values, like comma. It's a comma.
Comma.
Okay. Okay.
We already said that beta n is equal to beta p. We're just going forward from there.
Okay.
Okay. So what happens now? We start to say that for a given IDS n and IDS p, what will be the value of V out? Can we make that thing out? So V out is all those points where the current values are equal. Can we say this? Hello.
Yes, sir.
So how does this appear then? So the first point is, let us say, as we इसी में जाते हैं पहले. So where are the values equal? See, there is one intersection happening here. Are you able to see that? Then there is another intersection happening here, another happening here, and so on. So if we start to plot it like this, then this is the way our intersections would play out at different values of Vn. See, what am I doing? I'm changing the value of Vn. At different values of Vn, different curves would come into picture. There is this curve for the NMOS and this curve for the PMOS. So where do they intersect? At a value of Vn, they intersect at almost VDD. So Vout will be almost VDD when Vn is equal to 0.2. When Vin goes to 0.4, these are the two curves that come into picture, and my Vout will be almost equal to VDD, though not equal to VDD, slightly lesser than VDD there. You go to Vn equal to 0.6, and you see, array, the intersection point now has come to almost 0. You go to 0.8, and it is at 0. So now when you plot, it, you see that, okay, Vn 0, Vn 1, Vn 2, Vn 3, Vn 4, Vn 5, and you get what you call as the transfer characteristic of your inverter. Are you able to see this? Any questions?
So what will happen at VDD by 2, like when we have, it is not 0 or VDD?
Yeah, so at VDD by 2, we would probably have had this point.
Yes, sir. So what will be the output when Vn is
output
VDD?
is अगर इधर intersection हो रहा है तो यहाँ होगा output. तो इस range में हो रहा है तो यहाँ पे कहीं भी आगे पीछे देखो इतना सारा range है output का, कहीं भी होगा.
अच्छा, यहाँ फिर कहीं भी हो सकता है.
मतलब वो मूव कर रहा है. हाँ, मतलब वो आपके डिवाइसेस के ऊपर आपने एग्जैक्टली कितना मिलीवोल्ट ऊंचा नीचा के बेसिस पे वो आगे पीछे हो जाएगा थोड़ा सा.
Yes, yes. Okay.
Sir.
Yes.
Sir. So, sir, what we were doing is that for different bean values, we plotted the IDS curve for the PMOS and NMOS, and then the intersection points is the second graph, right? The red one.
Yes.
Okay.
So we plotted the intersection points over here, and then we say, ये अलग-अलग Vn की values के साथ ये intersection points आए हैं, I can simply plot them over here. That is my Vout.
Yeah, got it, sir.
That is how you make the transfer characteristic.
Yeah, and the intersection point was coming because of the Kirchhoff law needs to be.
Because of intersection of Vn1 for PMOS and Vn1 for the NMOS.
Yeah, the currents has to be equal, right?
Yes, currents have to be KCL.
Yeah, yes, got it, sir. Thank you.
Okay. So,
sir?
Yes.
So in the left graph, what were we plotting on x-axis and y-axis? Now on y-axis particularly, on the left side graph.
This is current, na? IDS. हमने बताया था ना IDSN and IDSP. Yeah.
Yes, sir. So why are we writing Vn2, Vn1 and all those Vs?
You tell me. Vn is equal to VGS value, na?
Yes, sir.
तो अलग-अलग VGS value पे हम IDS वाले curves plot कर रहे हैं बस. What else?
Okay.
See, this characteristic that you see is for different values of VGS, is it not?
Yes, sir.
But for any Vn value, there will only be one of these lines valid.
Yes, sir.
So for any Vn value, there is just one of these lines which is valid. And that is what we are showing.
Okay, sir.
Huh? So now at different points, A, B, C, D, E, F, A, B, C, D, E, where are my different transistors? So at A, my NMOS is in cutoff, CMOS is in linear. And you can actually fill this entire table like this. Can you verify if this table is filled correctly? Any questions, any confusion around it?
Sure.
Yes, Debajit.
Sir, can you explain? I have a confusion in region B and D.
in
the region B and D, where we are saying that
region B and D.
Yes, sir.
So, do you want to go back to the curves once again and see?
Yes, sir.
So region B is when your V in is between VDD by 2 and VTN. So let us say it is 0.4 of VDD. Is it okay? 0.4 वाला curve देखें. So you see what is happening? My NMOS isn't clearly in saturation. What about my PMOS? It is in linear.
Okay.
है ना?
Sir, one more. Okay, understood, sir. Sir, I had one more question also, that looking at the point in the graph, we can also predict the amount of current that would be flowing, right?
Yes,
or the
that is
discharge.
what IDS was ना. The IDS की value जो है vertical axis की जो value है, that is the amount of current that is flowing.
Okay. Yes.
So what is the amount of current that is flowing? Now tell me.
Sir, in B and D, the current through the NMOS would be very low.
So current A के दौरान भी बहुत कम होगा, E के दौरान भी almost zero होगा, है ना?
Yes, sir.
And B and D के दौरान थोड़ा सा
A little
होगा.
bit higher. Yes, sir.
थोड़ा सा होगा. And सबसे ज्यादा कब होगा? C के दौरान.
And okay, when the input is at VDD by 2.
When the input is at VDD by 2.
Okay.
So this is your current come. So there is no current when the input was 0 or when the input was 1. Only when the transition was happening, there was some current.
Yes.
Okay.
Thank you, sir.
Sir, in this current one, sir, when we had in the points B and D, then basically the PMOS and or either of the PMOS and was in linear, right?
Yeah.
So the current, so I mean, if except for when both are in cutoff, then some current will be flowing. So I'm not able to understand this curve actually. That
Which
you just
curve?
draw the so जब
ये
नीचे
वाला?
वाला बना, yeah.
हाँ, क्यों? क्या नहीं? देखो इसको वापस उसी कर्व से जाके देख लेते हैं पहले वाले से. So let us look at it over here, पुराने वाले में. So at this value, then let us say this is point A, Vn is equal to 0.2 is point A. What is
Yes,
the value
sir.
of current? It's almost 0.
Yeah.
I go to point B. What is the value of current now?
Okay, right. Okay.
This is the value, na? It is not 0, it is more than 0. Now, if I had a Vn is equal to 0.5, you will see that it would be somewhere here. The point of intersection would have been somewhere here. जो हमने यहाँ पे देखा था.
When both are in saturation.
इस range में है ना, the value of current is still higher.
When both are in saturation.
Yes. यही मैंने वहाँ plot करा था ये.
Okay. Okay. Yeah. Yes.
है ना? Clear? See, this is very important. देखो आपको ना, those of you who are MTech students, you probably already realize that you never got to see an inverter like this ever earlier. Did you?
Yes, sir.
So almost nowhere you will see inverter being taught in such detail and with such, कि कौन सा cutoff में है, कौन सा saturation में. But this is very important for you to understand. Even though we are talking about digital circuits, if you do not understand where your device is operating in, for example, you will not know how to make a capacitance, MOS capacitance. आपको यही नहीं पता लगेगा कि वो accumulation में कब गया और वो inversion में कब चला गया और where you should design your capacitance. So these concepts are really important. They will really help you become good circuit designers. So इस चीज के बारे में please be very comfortable with it. I can give you another circuit and ask you कि कौन सा device saturation में है and stuff like that. Okay. Typically interviews में inverter तो पूछ ही लेते हैं लोग. So good designers, when they interview you, they will typically end up asking you the transfer characteristics of an inverter somewhere in one question or another. Okay. So please be very well versed with this idea. So we have
So,
covered two critical concepts today. Elmore delay के लिए मैंने आपको कहा है कि आप please घर जाके numericals please practice करें. And this concept also, I'm saying that we have covered it in class. We are covering it. I'm trying to resolve all your queries. But even if you get queries again at home, you can read the book, you can review the lecture again. But please be very clear about this concept. Yes, there was a question.
yes, sir. So when both the devices like NMOS and PMOS are in saturation, I am seeing that I have the max amount of current. So that means that this will be the point that will be associated with the maximum power dissipation, kind of the most power will be right. So like, but what exactly is the utility of this region? I'm getting it, but is it like, because so this power is static power or the dynamic power? For example, this power, how will I say
So we're
this?
talking about DC analysis. So there's nothing dynamic in it yet.
Okay, so it's static power only.
If you will bias your inverter at this point, it will consume the maximum current. But do you realize it is also the most sensitive? A small change in input, 1 millivolt here or 1 millivolt there, the output will change, swing by 100 millivolts.
Yeah, yes, sir.
That's the importance of this point.
Okay.
Hmm?
So like, for example, like generally we say na ki the CMOS inverter has zero static power dissipation. It has only dynamic thing. But from here, I can see that no, there is some dissipation.
Yes, because we are over here talking about using an inverter as an amplifier. You see, that is where I'm saying if you put a small signal at C, what happens? Output would toggle from, you just toggle the input from plus minus 3 millivolts, output would toggle by plus minus 300 millivolts. Nahin?
Yeah.
It's amplifying 100 times. So when you want to use the inverter as an amplifier, then amplifier will consume current. But otherwise, if you want to use it as a digital logic, then you don't need to worry about the C point. C point will just come and go like this. It's so fast.
Okay, so like for me, the V in, for example, if I have to do for the digital circuit, so the V in will be basically the biasing voltage should be such that
No. In a digital circuit, V in will simply come from 0 and go to VDD. And let us say 100 picoseconds. So within 100 picoseconds, this A, B, C, D, E would have already moved.
Okay. So, but still this curve will get na, right? So the area between
curve will
this...
come and go. अब इसको ये तो देखो हमने अभी VDD के साथ plot करा ना. So you can possibly plot it with time. You can do it like this. So I say that ऐसा नहीं. So a typical question that I ask in interviews, I would ask in interviews would be that these are A, B, C, D, E. This is my input and this is time axis. Okay. I would ask people to plot the current waveform with respect to time. What would you do? The plot would actually come like this only.
Yeah.
This is just a different way of putting the question. Now you notice that if I improve the input slope, what happens?
Then this area would be much lesser.
Yes.
Okay, right.
This value remains same. But the charge that I consume, that I waste, reduces significantly. That is where when we will talk about power later in this course, we will talk about using good rise time and fall time.
Yeah, so the y-axis basically would remain the same, but the x-axis, the time would decrease. Yeah.
Yes.
Right.
If you have good rise time and fall time, you can reduce overall charge consumed in this transition because you have reduced the pulse width for this current curve.
Yeah. Yes, sir.
Okay.
Yes, sir. Got it, sir.
So this is something we will anyways cover later, but concept should, अब मैं clarify कर रहा, the concept should be clear for everyone now. Madhur, you have a question?
Yes, sir. So why were we talking about biasing in this circuit when we are making a digital inverter?
No, because if you want to make an amplifier out of an inverter, then we would want to talk about biasing also.
Yes.
An inverter is an inverter. It can operate like anything.
Okay, sir. So when we are making use of this inverter as a common source amplifier, then we are
Yes.
talking about biasing.
Not just a common source, simply saying an amplifier.
Okay, sir. And in digital, we won't pay much attention to this C region. We will just go from A to E directly.
So if your input slope is bad, as in the top timing curve,
yes, sir,
then the C region also becomes very important, because that C region would also exist for a long time. It will define the total current consumption, na?
Yes, sir.
So if your input is rising very, very slowly or falling very, very slowly, then the C region also is there for a long time. Then this kind of becomes time axis. So the charge that you consume, that is transferred from VDD to ground, that is wasted, increases. है ना? Power increases.
So C region doesn't seem to be appearing for a very long time. It is just a vertical, almost a vertical line.
अरे भाई ये तो VDD और VN का एक्सेस है ना?
Yes, sir.
मैं अब टाइम के साथ बता रहा हूँ. ऊपर देखो. If this is my curve, if this is my input waveform with respect to time, then the C region is going to be there for a longer time, na? In comparison to here.
Yes, sir. Yeah. Yes. Yeah.
That is what I'm talking about.
Okay, sir.
Okay.
Yes.
Yes. Gagandeep?
Yes, sir, can we also change this width of this current lobe by changing the width of the MOSFETs?
Yes, obviously, because as soon as you change the width of the MOSFETs, IDS and VDS would change. The hoga hi na? IDS and VDS are dependent on width. IDS is dependent on width of the device.
Yes, sir. So, sir, I have confusion in this thing only, that let's say that I want this to be a very, very fast transition inverter. So I say, okay, I'll increase BMOS by some amount and I increase the NMOS width by some amount. So basically, after increasing the width of the PMOS and NMOS, although this transition is very, very fast, but the current has also increased. So basically, I will now have more current through my MOSFETs.
So तुम्हारा confusion इसलिए है because तुम्हें driver का width और length width change करना था, तुम इस device का width change करना शुरू हो गए हो. This is the input transition, not the output transition. There is some other inverter driving Vin, na? To get a good slope on Vin, you have to increase the size of this inverter.
I need a good rise and fall time of the input.
Of the input, ना? तो अगर इनपुट का आपको राइज और फॉल चेंज करना है, तो जो इनपुट, ये इनपुट जिस इन्वर्टर का आउटपुट है उसका आउटपुट चेंज करना है ना आपने, तो इसकी पावर बढ़ेगी, इस इन्वर्टर की तो पावर कम ही होगी ना.
ओके,
समझे?
तो सर इसीलिए मतलब बैक टू बैक इन्वर्टर यूज कर सकते हैं, पीछे वाला बड़ा और अकेला छोटा.
नहीं. तो वो साइजिंग कैसे करेंगे अभी हम उस पे आते हैं. पीछे वाला बड़ा नहीं होगा. There is a logical effort वाला चीज, will come to that in probably the next class.